Hi, this is topic 3, and we're going to be talking about populations. So, how do ecologists study populations? Researchers are going to be using different things to study population. They're going to be using geographic range, which has to do with location, density, which means how many people are in a given area or how little they are, distribution, whether they're spread out or all together, growth rate, which is how many births versus deaths, and then age structure. So population density refers to the number of individuals per unit area. So that means how many people are different species are grouped together versus how many are spread apart. So different species often have very different densities. So you can have a high amount of snails in one given area versus frogs. Frogs would be a lot less than snails in that area. So even though it's the same environment. So growth rate depends whether the population size increases, decreases, or stays the same. So you can increase by having a higher birth rate versus death rate. You can decrease by having a higher death rate versus birth rate. And then you could stay the same by having the birth rate and the death rate stay the same. Age structure is the number of males and females of each age a population contains. So most plants and animals can't reproduce until they reach a certain age. For us, that's usually between 13 and up until maybe 45. That's usually the average, more or less, for menopause. But for a variety of animals, it just depends. Age structure graph tends to look like this. These are 4 different countries. This is the US, Spain, Germany, Guatemala. Um, the age structure graph, the way it works is you have the lower aged. So like this is 0 to 14 is a blue, yellow is 15 to 44, this is 45 to 85. Notice how it gets less the higher up you go. And that's because as you get older, you get a variety of diseases and old age starts to take a play. And then so you expect the higher population to be lower than the bottom part of the generation. Depending on the country, depends on whether they live longer or not, and that's because of healthcare, the environment, whatever it may be that's helping them stay alive longer. Then you also have males versus females, and that can be shown males on this side versus males on this side. So depending, like I said, on the country, depends on what it looks like, but age structures are basically very similar. You have the age um, always on the top is older, and then the younger age is always on the bottom, and then you usually have males on the left hand side, females on the right hand side, and you always want to see a higher number towards the bottom and the lower number towards the top. And then factors that affect population growth. So, like I said before, birth rate, death rate, and the rate at which individuals leave or enter the population affects population growth. So something we know a lot about in South Florida is immigration versus emigration. So a population will increase or decrease in size depending on how many individuals are added to it or removed from it. So if you get a lot of people coming in with immigration, that population is going to increase. If you have a lot of people emigrating or exiting, so emigrating, exiting, then you're going to have the population decrease. So a population can grow when its birth rate's higher. So as you continue to, if it's, I think on average right now we have 5 births versus 2 deaths um, every few seconds or so. So our population is steadily increasing. Exponential growth is under ideal conditions with all possible resources, a population is going to continue to grow. If you provide a population with all the food and space it needs, then it's going to continue to grow. In exponential growth, the larger a population gets, the faster it grows. The size of each generation will be larger than the generation before. So here's an experiment where you have an organism that reproduces very rapidly. So in this experiment, a bacteria is going to produce 2 cells every 20 minutes. So we start off with 1. After 20 minutes, we get 2. After another 20 minutes, we get 4. After another 20 minutes, we get 8. After another 20 minutes, 16, so on and so forth. So in an hour, we'll have 64 bacteria. In one day, we have that very giant number that I don't know how to say. And then if it continues to go, then the entire bacterial population will cover the Earth in a few days. So this is an organism that produces fast. And this curve right here is called a J curve. So that's usually how you know with exponential growth, or that you have exponential growth, when you have that J curve, because it's going to increase, 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 and keep going up. So as the population got bigger, it started getting a lot faster. Versus an organism that reproduces slowly. So elephants, their gestation period is 2 years. That means they hold the baby in the womb for 2 years. And they can only hold one offspring at a time. And it takes them 10 years to mature in order to have another baby, the newborn elephant. So if exponential growth occurs here, it takes them about 750 years to get to 20 million elephants. So here we started off not zero, but like a little bit above zero. And then at 250, we got maybe to like 1 million. And then at 500 years, we got maybe to 2. But after that, it got a little bit better. So around, I want to say 600, maybe 650, we got to 5. And then from there, it was so much easier to just build up into 20 million elephants. So sometimes when an organism goes into its new environment, it can grow exponentially for a short amount of time. Think about here in Florida, we have the Burmese python, which is an invasive species. That Burmese python, when it was introduced into the Everglades, it had all this food. It had no predators to it, still doesn't. So it has all this prey and it's able to eat, make a lot of eggs, and then it just keeps growing. So that population is able to grow very exponentially. And then we have logistic growth, which is when a population grows, growth slows and then stops. At first, it starts off as exponential growth and then it kind of just slows down. So natural populations don't grow exponentially for long. So at some point, we run out of resources or space or different things like that. And then so you get something like this. This is called an S curve. So logistic growth usually is referred to as an S. It's a very stretched out S, but it's still an S. So you have the J curve happening here, and then it's going to start slowing down. And once it reaches this part of the carrying capacity, which is that line, it's going to kind of just go up and down that line. It might go a little bit above, it might go a little bit below, but it's kind of stabilizes into that. So that carrying capacity is basically if you picture your hands and you're trying to fill it up with M&Ms or peanuts or whatever you want to picture, you have your hands cupped and then you pour that in. There's only so much you can hold. After a while, it starts kind of going over your hands. That's the same idea with carrying capacity in a certain environment. You can only hold so many, and it can go up to, let's say we have 50 is the maximum carrying capacity. You can go to 53, then you can go down to 42, then you can go back up to 56, but it's going to kind of play that line on the carrying capacity. So there are different factors that determine carrying capacity. Acting separately or together, limiting factors determine the carrying capacity of an environment. So these things are, some of them depend on population density and some of them do not. Like the ones that do not, usually it's natural disasters that cause them. So limiting factors that depend on population density are competition, predation, herbivory, parasitism, disease, and stress from overcrowding. So these density dependent, that means depending on the population, depends on whether these factors are there. So once it reaches a certain area, these factors will happen and then it can decrease the population. So competition happens when places get too crowded. So if individuals are competing for food, water, space, sunlight, and other essentials, then they're going to try to survive and they want to survive and reproduce. So they're going to compete with one another to get that, whatever it may be. predation and herbivory, that helps with reducing the amount of the population. So if there's a lot more prey and not a lot of predators, as the predators start eating most of the prey, the predator numbers are going to increase while the prey numbers are going to decrease. Same thing happens with herbivores on plants. If there's a lot of plants, then there's going to be an increase in herbivores and a decrease in plants. So this is a predator-prey relationship. This is one of a wolf and moose population on Isle Royale over the years. And as you can see it, you see that the blue line is the wolf, and then the red line is the moose. So around 1980, the number of wolves, which was 50, that was basically the highest point of it. And that more than likely is their carrying capacity. But they had an outbreak of a virus, probably caused by the population density. And then that caused them to dramatically decrease. They got to maybe about 11. The moose population kind of just stayed level. But right after that virus outbreak where it caused the wolves to go way down, that means the predators decrease. So what ends up happening to the moose? They end up steadily increasing until they get to about 2,400. That's likely their carrying capacity because as soon as they hit that, they dramatically decreased. Either by the wolves, because the wolves were eating more, or they had some kind of other outbreak or competition. They ran out of food. It could be multiple things as shown by the density dependent limiting factors. So herbivore effects, once again, the moose, they were eating all the plants, therefore their population decreased. Humans were also predators. We cause a lot of issues by overdoing things. So fishing fleets catch more and more fish every year. So we overfish. So that causes higher death rates versus birth rates. That causes a decrease in all the fish population. So we need to cut back on fishing in order to increase and let that population increase. Parasites and disease causing organisms feed at the expense of their host, weakening them and cause disease or death. So ticks feeding on the blood of a hedgehog or a dog, that can transmit bacteria that causes disease, which then will lower that population. And then we get stressed from overcrowding. So usually when we get back to school, we have a lot higher amount of population compared to what the summer usually is. And there's a large grouping of people. And what ends up happening with that high level of people is it weakens the body's ability. So we're getting more viruses and bacteria and different things like that, which in the beginning of the year, usually people get sick more often than before because we were at home or we were surrounded by only our family, maybe some other family members, maybe friends, but not as much as we do when we're in school. Density independent limiting factors usually they don't depend on at all on population density. So they're unusual weather like hurricanes, droughts, or floods, and natural disasters such as wildfires. They don't care how big your population is. They're not going to pinpoint. They have no conscience in order to pinpoint, be like, hey, I can kill more things in that area than that area. They don't do that. They just hit an area because of whatever allowed it to hit that area. So a hurricane will hit Florida just because the warm waters around us help feed it. So then it tends to hit Florida. Wildfires tend to happen in the Everglades because the area gets dry. It's just perfect conditions to cause these things. Severe drought can kill off a large number of fish in an area. That can be because of extreme heat. So the conditions have to be right. And that's it.